All right, today we're going on a quest. Not for some buried treasure, but for something that can be just as tricky to find. The true value of something. We're going to pull back the curtain on what seems like a simple act, measuring something, and discover the incredible and kind of complex science hiding just underneath.
So let's just kick things off with the biggest question of all, one that's going to guide this whole explainer. Can we ever know the exact length of a table, or the precise temperature of the air? I mean, is a perfect measurement even possible? You might think so, but the reality is way more interesting than just a simple yes or no.
Okay, let's dive right in. So where do you even start? Well, every single quest for a measurement begins with a choice. You have to pick your weapon, your instrument. And trust me, this decision is way more important than you probably think.
At its very core, a measurement is really just a comparison. That's it. We take something we don't know, like the length of a pencil, and we hold it up against something we do know, a standard, like an inch or a centimeter. The instrument is just the bridge that lets us make that comparison and stick a number on it.
Now, here's where it gets really interesting. How do we actually get that number? Well, our tools basically fall into two main camps. You've got your analog stuff, like an old-school mercury thermometer. You have to kind of squint and judge where that red line is sitting between the tick marks. But with a digital tool, it just flashes the numbers at you. One requires your best guess, the other gives you a hard number, but that doesn't mean it's more right.
So first things first, you have to check the instrument's range. It sounds super obvious, right? But it's the first filter. Can your tool even handle the job? You wouldn't try to weigh a single feather on a massive truck scale, and you definitely wouldn't measure a football field with a tiny 6-inch ruler. Your tool has to be playing in the right league for what you're trying to measure.
Next up, we have sensitivity. Now, this is all about the level of detail. Think of it as the finest of the fine print your tool can actually see. A ruler with little millimeter marks, for instance, is way more sensitive than one that only shows centimeters. This one quality sets the absolute limit on how precise you can possibly be.
And finally, for this part, we've got responsiveness. This is all about speed. How fast does your tool wake up and show you a new number when things change? If you're measuring something that's changing fast, say the temperature of a wild chemical reaction, a slow, old-fashioned thermometer is just going to give you ancient history. The number you're reading is already wrong. You need a tool that can keep up.
All right, so you've picked the perfect instrument. It's got the right range, it's sensitive, it's fast. You are ready to nail that one true value. Well, this is where reality comes crashing in, because every single measurement we make, without exception, is imperfect. It's haunted by the ghost of error. I just love this quote because it completely flips how we should think about this. An error isn't a mistake you made. It isn't a failure. It's a fundamental part of trying to touch and quantify the physical world. The second you try to measure something, you introduce a little bit of fuzziness, a little bit of uncertainty.
But here's the thing. Not all errors are the same. They come in two main flavors. To understand this, just picture an archer. A systematic error is like the sight on their bow being misaligned. Every single arrow they shoot hits the target, but they all hit high and to the right. It's a consistent, repeatable error. Now, a random error, that's like a sudden, unpredictable gust of wind. Their arrows land all over the place, scattered randomly around the bullseye.
And this is a perfect example of a systematic error. It's called parallax, and you've definitely done this before without even thinking about it. Just look at this dial. If you look at it from the left, the needle looks like it's on a lower number. From the right, it looks higher. The only way to get the true reading is to look at it dead on, straight from above. If you aren't doing that every single time, you are systematically skewing your own results.
So if every measurement is plagued by these random errors, these little gusts of wind, how can we ever trust anything? We can't stop the wind, but we can learn how it behaves. The key is to stop looking for one perfect shot and instead embrace the power of taking many, many shots.
This is a huge mental shift, right? We're not hunting for that one correct number anymore. No way. We're becoming detectives. We're gathering a whole bunch of clues, a set of different measurements, and when we put them all together, they start to tell us a story. They point us toward the truth.
So you do it. You measure that same little block over and over and over again, and you get a list of numbers that looks something like this. See that? They're all dancing around the same value, but none of them are exactly the same. That's random error right there, out in the wild. Little wobbles in your hand, slight changes in how your eye lines up. It all creates this beautiful, messy data.
So what do we do with this cloud of numbers? Well, the very first thing is to find the center of that cloud. We calculate the mean. You probably know it as the average. You just add them all up and divide by how many you took. It's simple, but this number becomes our single best guess, our best estimate of that true value we've been hunting for.
And here's where it gets really cool. If you start to plot all those different measurements, maybe by grouping them into little bins like this, you get a shape. A pattern emerges from the randomness. Notice how most of the measurements are all clustered together right there in the middle, right around the mean we just found. Our data is actually telling us a story.
Okay, but knowing the average isn't the whole story. We have our best guess, but how good is that guess? I mean, are all our measurements huddled together really tightly, or are they spread all over the place? That's where standard deviation comes in. It is an incredibly powerful number that measures the spread or scatter of your data. Think of it as a confidence score for your average. A small number means high confidence. A big number means, well, your guess is a lot more uncertain.
So we've chosen our tool, we've wrestled with errors, we found the center of our data, and we've even measured our own uncertainty. Now for the final and maybe most important step. How do we report what we found in a way that's actually honest?
You do your math, you hit equals on the calculator, and bam, it spits out this number, 15.789345 grams. Wow, look at all those decimal places. It looks so incredibly smart and precise, doesn't it? But you know what? It's a lie. It's a flat-out lie because it's pretending to have a level of precision that your tool and your method just can't back up. And this brings us right back to the beginning. It all comes full circle with this idea of significant figures. The rule is simple, but it's fundamental. The number of digits you write down has to reflect the sensitivity, those little tick marks, on the tool you used in the first place. You can't just invent precision with a calculator. So you have to be honest. You take that crazy long number and you round it properly. It becomes 15.8 grams. Now, this is a true number. It tells the world, hey, I'm certain about the 15, and I'm making my best estimated guess on that final digit, the 0.8. It communicates the value, but it also communicates the quality of that value. And that brings us here, to the summit. This is the final result. This is how a real scientist reports a measurement. Look at it, it's beautiful. It has two parts. First, our best estimate, the mean, 25.4. And second, our statement of honesty, our uncertainty, plus or minus 0.1. This little expression tells a whole story. It says we think the real value is 25.4, and we're really confident it's somewhere between 25.3 and 25.5. So let's end right where we started, with a big question. If all of our scientific knowledge, from the size of an atom to the distance to the stars, is built on measurements that always have uncertainty built right into them, what does that say about reality? Maybe the truest wisdom isn't about finding one perfect, flawless answer. Maybe it's about understanding and even respecting the limits of what we can know for sure. Something to think about. Thanks for joining me.